Within this video, we're going to look at a bonding model described in Chapter 9. Chapter 9 begins by considering VSEPR theory. We want to be able to draw Lewis structures, determine electron and molecular domain geometries, predict ideal bond angles, and distortions from those ideal bond angles. Consider the shape, and be able to determine whether molecules are polar or nonpolar. This involves drawing the Lewis structure, determining the VSEPR predicted geometry, and considering then the shape of the molecule. In sections 9.4 and 9.5, we're now going to move to describe a more advanced bonding model. Within this, we want to explain the role of what's called orbital overlap in the formation of covalent bonds and determine the hybridization of atoms and molecules based on the observed molecular structures. What is a covalent bond? It has to involve electron density found between the atoms. How do we describe this electron density? Well, in a Lewis structure, we use simple dots, and we showed them as being found between the two atoms, leading to some degree of sharing. So what does the symbolism represent? What does the symbol H represent? What does the dot represent? What are the dots between the atoms representing? Well, for the hydrogen, that's an atom with one valence electron and one proton. And we're seeing that two electrons are being shared between the atoms. But if we think back to Chapter 6, electrons are a lot more than just a dot. Electrons, after all, are found in atomic orbitals. And we spend a lot of time and effort describing these atomic orbitals, including radio probability distribution functions. Now we're going to begin to bring these ideas together, a more advanced treatment of atomic orbitals, and how we can now combine orbitals to describe bonds and where the electron density is found. Within Lewis theory, we are drawing these pictures and we are placing electrons between two atoms. In Lewis theory, the covalent bonding occurs when the atoms were sharing electrons because we had electron density being found between the two nuclei, and a given electron could be attracted to protons in each atom. Within valence bond theory, we'll be doing something similar. In valence bond theory, we'll be considering the buildup of electron density between the two nuclei when we consider how valence atomic orbitals share space or overlap with another valence atomic orbital. The overlap of the orbitals will allow two electrons of opposite spin to share that region of space between the two nuclei, forming a bond. This idea of two electrons of opposite spin, if that sounds like the Pauli exclusion principle, it is. This is now, instead of saying electrons are dots, let's place them back into atomic orbitals and see how those atomic orbitals can come together to form covalent bonds. The overlap of orbitals allows two electrons of opposite spin to share the space between the nuclei, and the net attractions then will form the bond. So let's consider the bonding in things like H2, HCl, and Cl2. If I think about H2, the orbital diagrams, those are where I draw a sketch to show the electrons and the spin direction. If I have a 1s electron that spin up, and on the other atom, a 1s electron spin down, I could bring both of these together and have overlap of the atomic orbitals. Two electrons could now be found in the region in between, forming a covalent bond. The bonding in HCl, I have to consider the electron configurations and the valence electrons. Hydrogen is 1s. The chlorine, I see a total of 5 valence electrons. One of them is unpaired, so I could then have an overlap between both of the hydrogen and the chlorine, and I could form a covalent bond there. I'm considering both the arrangement of the atomic orbitals and whether I have unpaired electrons. In Cl2, I could be bringing together a 3p atomic orbital with another 3p atomic orbital. That could be leading to electron density now found between the two nuclei. So take a second, reflect on this. We need to be able to use the periodic table to find electron configurations, especially for the valence electrons, and be able to draw and interpret orbital diagrams like these. Take a second, reflect on that skill. Is that something you're able to do? Are you able to quickly recognize how to use the periodic table to get sketches like these? Share your ideas. Let's add to that now and consider what are called hybrid orbitals. If you recall, the atomic orbitals, they came out of our Schrodinger equation when we were analyzing the hydrogen atom. To move beyond this and explain the bonding that we have within molecules, we're going to employ this idea of hybrid orbitals. The examples that we just looked at, H2, HCl, Cl2, hybrid orbitals were not necessary. But I'm going to now show us a few examples where they're going to be needed. When we're looking at hybrid orbitals, it begins by being able to draw a Lewis structure, consider what the VSEPR predicted geometry is, and now explain that using what's called valence bond theory. We saw how valence bond theory could describe the bonding in H2 or HCl by seeing how the atomic orbitals overlapped. Now we're going to add to that a different idea. We're going to see that there's times when we need to make new orbitals, which are called hybrid orbitals. Hybrid orbitals will be able to explain geometries that the simple atomic orbitals will not. Hybrid orbitals are going to be used to explain the electron domain geometries. And we don't always need them, but we'll need them when the simple bringing together of atomic orbitals is not sufficient. Let me show you what I mean. Let's say we're trying to describe the bonding in beryllium with two fluorine atoms, the covalent bonding in BeF2. So here's an initial Lewis structure for that. Here's a picture from the e-text, a figure from the e-text describing how we can have the overlap of orbitals that will explain the bonding. If I look at this, the features on the outside, those fluorine atoms, those look very similar to what I just did. They're saying that we could have an unpaired electron in a 2p atomic orbital. Those atomic orbitals could be properly aligned that would then lead to this covalent bonding. If I look at the orbital diagrams for the fluorine, they're making sense to me because in each case I have an unpaired electron that could be used to form that covalent bond. But if I look at the beryllium, it's a different story. Here are the valence electrons for beryllium. Beryllium is 2s2. Do you see why I can't use my previous approach? Why wouldn't I simply be able to take this and combine them like I did in H2 or HCl or Cl2? Within your analysis, why can't I just see how the atomic orbitals somehow overlap to give me covalent bonds? Share your answer. A leading thing that I see here, I don't have any unpaired electrons in beryllium. If I'm looking at the overlap of how I can have the electrons that are unpaired, spin up, spin down in different regions between the nuclei, that's not what I have in beryllium. In the ground state, they're both paired up. I don't have any unpaired electrons. So what will it mean to sort of change the rules and look at this differently? So the first thing I'm going to do is I'm going to bring one of the electrons over and put it into a 2p instead. Now I have two unpaired electrons. Next thing I'm going to do is, instead of having them in an s orbital and a p orbital, I'm going to begin thinking about a new type of orbital, something called an sp orbital. I have two sp orbitals and two p orbitals. sp, that's a description of what is called a hybrid orbital. Let me show you how this works. This description right here, that's what the figure is describing. It is showing how that you can have two sp hybrid orbitals, each with an unpaired electron, which can now overlap with the 2p atomic orbitals to lead to the covalent bonds. If we know the electron domain geometry for an atom, we know the appropriate hybrid orbitals that will work. If I am seeking to explain a linear geometry, two electron domains, I'm going to combine an s orbital with a p orbital and form two sp hybrid orbitals. Here they are, and when they show them both in the same overlapping region, that's what they're showing here. One of the lobes is pointing to the left, one's pointing to the right. Combining an s orbital and a p orbital results in two sp hybrid orbitals. So I'm going to use sp hybrid orbitals whenever I have two electron domains. What if I'm seeking to explain three electron domains? I will combine an s orbital with a p and with another p. That gives me three sp2 hybrid orbitals. If I'm seeking to explain a trigonal planar electron domain geometry, I will use sp2 hybrid orbitals. If I'm seeking to explain a tetrahedral electron domain geometry, I'll combine an s orbital with a p, with another p, and with the final p. That gives me four different sp3 hybrid orbitals. Notice the total number of orbitals is not changing. I'm just combining them in different ways. I'm combining them in different ways because I need to explain different electron domain geometries. So we begin with the Lewis structure, we do a VSEPR analysis, and then we can explain the bonding using valence bond theory. Let's see how it works with something like BF3. So begin, pause the video. What is the electron domain geometry for that central atom? I see three electron domains. That tells me it's a trigonal planar geometry. If I need to explain the bonding in three electron domains, if we think back just a moment ago, that's explained using sp2 hybridized orbitals. Three electron domains are explained with sp2 hybridized orbitals. Now tell me, sketch the orbital diagram for boron and sketch the orbital diagram for fluorine. Takes the valence electrons, how do they look? This would be my description for what boron looks like and for what fluorine looks like. In terms of the fluorine, I think this is going to be well suited to form a single bond because I see an unpaired electron in a p orbital that could then overlap with a orbital from the boron. But with the boron, I see some issues. This would be telling me that I only have one unpaired electron. That can't be right. I need to somehow get three unpaired electrons. Also, in the initial orbital diagram, there's an s orbital, a p, and another p. Those don't seem to explain the bond angles that I need to have. The bond angles within the BF3 are trigonal planar. They're all 120 degrees. If I look at these initial atomic orbitals, I don't see any angles that are 120 degrees. So I'm going to use hybridization. After hybridization, notice I still have a total of four orbitals. Three of them are sp2 hybridized, and I have a leftover p orbital. I've also taken one of the electrons and promoted it over, so I have three unpaired electrons. This is exactly what I need. If I have combined an s atomic orbital with a p and another p, that gives me three hybrid orbitals. They're all arranged in a trigonal planar geometry. They're all 120 degrees from each other. I have a single electron in each of those. That's exactly what I need that can now overlap with the 2p atomic orbital for the fluorine and form my covalent bond. So let's give it another try. What is the electron domain geometry for these atoms? The first carbon, the second carbon, and the oxygen. What is the electron domain geometry for each of those? The first one appears to be tetrahedral with four electron domains. The second is trigonal planar with three electron domains. The oxygen is tetrahedral. Let's be careful. We're looking at the electron domain geometry. I have two sets of lone pairs and two single bonds. That's a tetrahedral electron domain geometry. If I know the electron domain geometry, I know the hybridization. That first carbon is sp3 hybridized. The second one is sp2 hybridized, and the oxygen is sp3. If we can look at the structure, a Lewis structure, and determine the electron domain geometry, right there we know what the hybridization is going to be. Here's some suggested problems where you can begin to apply these ideas. in 9.51 and 9.52. It's given us a formula. Have to draw the Lewis structure, consider then what the VSEPR predicted geometry is. Based on the electron domain geometry, we know what the appropriate hybridization is going to be. Both of those are really excellent sets of problems, very typical of what you could find on an exam. Give those a try. If you get stuck on one, share your work. Let's discuss that. In 9.7, an image is given. It asks, what is the hybridization at each carbon atom? Let's see if we can do that. The idea that we're going to have to then develop a little bit more, how do we begin to use this theory to account for double bonds, triple bonds? That's something that we will move on to continue to examine and see how double bonds and triple bonds are part of valence bond theory as well.